will not make such a big deal out of it because there's so much one can say about that. Yeah, that could be more than 10 hours in itself. But anyway, I have it anyway for completeness. And then after that, I go on to higher dimensional black holes. So far, we have only been concerned about the classical description of black holes. Because we have only been using general relativity. And now the idea is, now we want to take into account quantum effects of black holes. This brings us to the 1970s, finally. There's a general lesson for quantum field theories. Namely that if you take a partition function for quantum field theory at finite temperature, T, then you can compute this partition function using the path integral the Euclidean path integral of the Wig-rotated quantum field theory. So what does this mean? Well, you make this Wig rotation of your quantum field theory. So you say that temperature is equal to I times some Euclidean time. So this tau is Euclidean time. That, of course, if you then express, say, the Minkowski metric in tau instead of t, then you get a four-dimensional Euclidean space. So you have now a completely positive signature and everything. And then what you do is you say, because I haven't mentioned the temperature yet, right? So then what you say is you say that this Euclidean time should have period beta equal to the inverse temperature. So you have some, to write it up in a formula, we can say that the partition function as function of beta or inverse temperature is equal to, the integral, the path integral, say if we integrate over a field phi could be anything we want, but just call it phi. Then we take the Euclidean action, so the Wig-rotated quantum field theory, as a function of phi, and then we integrate over all field configurations where tau is periodic with period where the fields are periodic in tau with period beta. So if you perform this half integral, that is equivalent to computing the partition function of final temperature T. And this is something used in quantum field theory. But now we can use this as a trick to understand what is the temperature of black holes. So if we consider the Schwarzschild black hole, then once again I can write the metric. That's the angular part here. So if we now do this Wick rotation, we can see that this, this Wick rotation here, we can see that this becomes the following positive signature metric. So that's nice, but let's try to do this near the black hole. And if you remember yesterday, we had this way of, we found this result for the metric near the black hole, right? So we're using this new coordinate x. So near the black hole, we found that the metric. So this is. Now we are back before the Wick rotation, so we're back in normal physical space. We found that the metric of the Schwarzschild black hole near the event horizon looks like this. And again, that's the angular part here, where this is this Brinkler space. Right? So what we want to do now is to Wick rotate that instead. So if I Wick rotate this, it's of course not very difficult. So then I get this metric. And now you see, well, this part here is unchanged. So this is just a two-sphere with radius r0. Nothing happened here. But over here, this you can recognize as something that looks like polar coordinates. So this looks like a two-dimensional Euclidean space in polar coordinates. But it's not exactly true always that this is Euclid, two-dimensional. I mean the plane in polar coordinates, because if it should really be that, then this tau coordinate should have a specific period. Because if it doesn't have the right period, tau should play the role of the angle in the polar coordinates, and x should play the role of the radius. But if you don't pick the period of tau to be correct, then you get a conical singularity. And that means that you have a singular metric. So that of course we want to avoid. So you can see, I mean, you can define now, say, we call the angle that we want to use alpha. You can define alpha to be kappa times tau. Then you can see that this part of the metric becomes now x squared d alpha squared plus dx squared. And then it's really, if you think of x as the radius and alpha as the angle, then it's really just polar coordinates, right? So you want this alpha to avoid the conical singularity at x equals 0. You have to pick that alpha has period 2 pi. Otherwise, there's conical deficit or conical, the opposite of that. And this means, so if this has period 2 pi, we see that we can just divide with, multiply with kappa. Not divide, sorry. We see that tau has to have period 2 pi divided by kappa, right? If we want to avoid this conical singularity. And then in this analogy, we have that the period of tau is equal to the inverse temperature. So this has to be equal to the inverse temperature. So, in other words, we have derived that the temperature of a black hole should be equal to the surface gravity kappa divided by 2 pi. So this is the Hawking temperature of a black hole, and you can perhaps immediately see that we can do exactly the same for the Kerr black hole, because we also have for the Kerr black hole that at least this part we could write like, I mean, we had the two-dimensional render space also for the Kerr black hole. This part looked a little different, but that's irrelevant for this purpose. So we can do exactly the same game for the Kerr black hole, and we again get that the temperature of the Kerr black hole is equal to the surface gravity divided by 2 pi. Then just the surface gravity is slightly different in terms of the parameters of the solution. So just to be specific, so over here we have the surface gravity for the Schwarzschild black hole was this, right? So this gives that the temperature for the Schwarzschild black hole is equal to 1/4 pi R0. I did everything correctly. Yeah.
So wait, why do we want the first bit of the metric to be exactly polar coordinates? It doesn't. I mean, it seems like we're choosing the temperature in order to be able to interpret the metric in a way that is convenient to us.
Yes, but that it might seem like that, but that's not really the case. So the way you should understand this is that independently of how you write these coordinates, I mean, once you're in Euclidean space, I mean, you can also think of this whole geometry here in Euclidean space. You don't have to go near the horizon. Once you're in Euclidean space, all you demand is that the solution should be free of singularities. And that means you're forced to choose this periodicity of time. So this is just a clever way to see how to avoid the potential singularity that you have.
So now we found temperature here to arise as this one. Yes?
Yeah.
But it's not the same everywhere.
So yeah, I'll come to that now. I think. Well, I'll come to that in a moment. Okay.
Sorry, is it any surprise that there's some form of singularity at x equals 0? Because x equals 0 corresponds to us looking at r equals r0, right?
Yeah.
So it sounds to me like purposefully avoiding a conical singularity at x equals 0 is a little bit odd because there kind of exists one there anyway, because that's you can't resist that position.
Yeah, but now you're thinking in the Lorentzian geometry, the actual real black hole geometry, where it's, the singularity is not actually I equals 0, as you know.
No, it's a
it's
a coordinate.
R0,
Yeah.
0. But this is in Euclidean space, and it's like we want to try to make sense of this statement for black holes, and then we have to go to what you call the Euclidean section of the metric. So it's if you want, it's a totally different space.
Okay.
This geometry and that geometry are two completely different geometries that have completely different properties. For one thing, the signature is different. So when you analyze this, you sort of have to forget about what you knew about the other one. It's a completely separate game. So we want now to make sense of this Euclidean section where we rotate it. And then we can see that if we want it to be singularity free, then it precisely fits with picking a certain period. And the interpretation of that is then that picks a certain temperature of the black hole. There's other ways to find this temperature, of course.
So then why we are allowed to do this reflection? Because it's useful, and we got something different what we had before. So why we are allowed to do this and talk again about our black hole?
Yeah, that's maybe a very philosophical question. I don't know, but you could ask the same for the quantum field theory. Why are we allowed to make
but there is
big
theory,
quotations for
I
quantum
think
field
Hart's
theory?
theorem or some mathematician's theorem that you can do and you will get the result. If you calculate partition function, I can't do it, but when you play this metric.
No, but I sort of agree with you in the sense that it's not all metrics you can actually do this for example. So I think for now the best way to think of this is that this is a nice direct way to understand why black holes should have a temperature. You cannot use this for any geometries, because not all geometries it's possible to understand the Euclidean section. Like, for example, if you have rotating black holes, you can already get in trouble. So, or if you have charged black holes in principle also. But as long as you stick to the geometry near the horizon and things like that, you're okay.
Sorry, one last thing. Could you quickly remind me why tau is capped by beta, whereas t is not?
Well, that's just because, so you have to think of the complex plane, right? So you have t here and tau here in the complex plane.
Yeah.
So and this is also for quantum field theory. So you have that tau is periodic with so if you go up here, then you come back here, right? So the theory is copying itself in this direction. It's periodic in this direction, but this doesn't say anything about what happens along the usual time direction.
Oh yeah, okay, sure.
Okay, so you know, this is a it's not a perfect analogy, but I mean, it gives a nice direct way to understand why black holes should have a temperature, and it also, I mean, people have been using it for many other things as well that I won't come into. Like for example, it gives a way to study black holes in 2 dimensions, and all kinds of things. But anyway, it's a long subject. So let me instead answer the other question that was before. So because we have actually assumed, I mean, we have been looking at the proper time. I mean, we have been assuming that the observer uses the time t, right? So this corresponds, as you know, to having the observer at r going to infinity, so far away from the black hole. But we could also look at an observer which is at r equal a constant. And then you have to, for that observer, he has a different time coordinate, I mean proper time natural to him, because he will have a proper time t prime, which is equal to this in terms of t, and this gives a different black hole temperature. So then there would be a redshift factor like this. And this is something known as the Tolman law, which is basically a law telling you how the temperature changes as you change to a different observer. So the observer we have been using over here, I mean, this temperature is measured at asymptotic infinity. So far away from the black hole. But we can measure it anywhere else as well. And in particular, we could measure it near the black hole. And then, if you use this definition of this x-coordinate that I was writing yesterday for the Schwarzschild black hole, then you actually get that close to the black hole. This factor becomes 1 over kappa x. So you just insert this definition of x here in where the r coordinate is. Okay?
So if the observer is near the horizon.
Yeah, so this is observer near the horizon. Observer near event horizon. Yeah, thanks. Then we change to the x-coordinate, and then this redshift factor becomes equal to that. And then you can see this is nothing but 1 over 2 pi x. Okay? And if you remember, yesterday we computed this acceleration for an observer close to the horizon. So that acceleration was 1 over x, right? So you see that it seems you have some sort of general relationship between this temperature and the local acceleration. So the local temperature and the local acceleration, which is that the local temperature is related to the acceleration divided by 2 pi. And this is something called the en route temperature, which is very roughly speaking, it means that if you have an accelerated observer, then for that observer you have something called an acceleration horizon. And that horizon will also have a temperature, and that temperature is then given by this. This gives another way to view the derivation of the Hawking temperature, because you could say, assume that I know that an acceleration horizon has such a temperature for this given acceleration. Then I know that the black hole has the acceleration, that is what we call the surface gravity kappa, as seen from an observer far away. And then the en route effect would say that this should be the temperature of the black hole measured from an observer very far away. So it's sort of another way to, you can use it as another way to view the Hawking temperature. So it's hopefully all consistent. Then I haven't really talked about Hawking radiation, and I'm not gonna say much about it. But what Hawking did, and many people after him did, was to analyze quantum field theory in curved spacetime. And if you study that, you find out that somehow the curvature of the spacetime can be responsible for radiation effects in the sense that, I mean, just to be very more specific, I just have to make a very general statement, but for the black hole case, what he found was that that from the horizon there is a black body radiation emitted from the event horizon. With temperature given by this Hawking temperature. So when you include quantum effects, the black hole is not really black because it actually emits radiation. You can say that maybe you can call it a black hole because it's a black body radiation, but even there you get in trouble if you look more closely, because actually there's something called the gray body factors which alter this radiation, because it's true that it's perfectly black body radiation when you're near the horizon, but then when it actually reaches the observer at infinity, it sort of has to go through a potential barrier created by the geometry around the black hole. And this gives a different spectrum. This changes the spectrum away from the black body radiation spectrum, and you call the sort of factor it changes with the gray body factor. Because just to say that it's not completely black body radiation. So it's more like gray body radiation area. So some of you might want to know a lot more about this, and if I had 30 hours of lectures, I would probably go through that as well, but I have to make some choices here and there, so I will go on to something different. I will now apply these results because all this means that you can define the thermodynamics of a black hole. Because now we found out that black holes have a temperature, working temperature, and this is seen from this observer at infinity. And then Bekenstein and Hawking postulated then that this means that the black holes will also have an entropy. And this entropy should be equal to the area of the black hole divided by 4T. And the simple reason why that should be is that then the three laws of black hole mechanics becomes the three laws of thermodynamics. Right? So the zeroth law, so now I just translate the three laws we had yesterday. The temperature is constant on the horizon. And this is, you can regard as some sort of equilibrium condition, right? So that you're saying the black hole should be in equilibrium, so therefore the temperature should be constant all over the event horizon. The first law is nothing but the change in the mass of the black hole should be equal to the temperature times the change in entropy. And then if we included the Kerr black hole, we would also include the angular velocity and the angular momentum. Then finally, the second law so here there's an issue. That is actually not immediately obvious how you should translate the second law, because what it says is that the S is a non-decreasing function of time, right? But obviously that cannot be true, because you also know that the black hole emits radiation, and then that takes out some of the energy of the black hole. So actually, then the entropy of the black hole would decrease. So the way that they resolved that, I mean, so it's true in classical GR still, but it's not true when you take into account Hawking radiation. So the way that Bekenstein resolved that is to say that that's fine, but then we just define a different entropy, namely to say that the total entropy is equal to the entropy of the black hole. Maybe I should put that here, the black hole. The total entropy, say if you have a universe with a single black hole in, is the the entropy of the universe is equal to the entropy of the black hole plus the entropy of all the rest. So the universe outside the event horizon. And this is very nice because in this way we actually resolve, at least in principle, this problem we had with the missing entropy. That I mentioned yesterday, because now we actually have a entropy for the black hole which can be macroscopically large. So if something is absorbed, something from the universe is absorbed in the black hole, then it's at least conceivable that the entropy can still be a non-decreasing function of time. Of course, then the whole problem is how you make sense of the macroscopically large entropy for a black hole which only has very few parameters, as you remember, because of the uniqueness theories. But then somehow the quantum degrees of freedom should that you don't really see in classical GR should somehow give a macroscopically large entropy. And I'm sure you all know that that's something people still work on. Of course, there's a problem with this. There's many problems, but one other problem is that normally you would say the entropy should scale like the volume, right? Because it's an extensive quantity. But for black holes, entropy scales like the area, and this is where all the the new physics comes in of black holes, because then you have to find a way that you can make sense of some degrees of freedom which don't sort of fill out it cannot really be very local degrees of freedom, where each degree of freedom sits in a little separate localized box, right? Because that would automatically mean the degrees of freedom should be, the total number of degrees of freedom of the black hole should go like the volume of the black hole, not the area. So somehow for a black hole, the degrees of freedom should more sit out on the event horizon, and then if you count all the degrees of freedom somehow, you get something proportional to the area, and that is related to all this big holography set. So this is a problem in the sense that you don't know how to really, you don't really know, well, at least at this point, maybe now we can say we know. You didn't know how to understand this. Maybe with the holography you can sort of, you have a framework where you can understand with this better. But then, so that's more like a problem of how to compute this and how to find these quantum degrees of freedom. But then there's a much worse problem, namely the information paradox. So what is the information paradox? Very, very briefly. So suppose we take we start with a universe without a black hole. So we have some star in that universe. There's no black holes anywhere. Then this star goes into a supernova and all that. And eventually, if we started with the right type of star, it settles down into a black hole. Then this black hole starts radiating, and eventually it has radiated away all its energy, and it evaporates completely. So what do we end up? Well, that's in some sense the question, but at least we know we end up with some Hawking radiation. And then no horizon anymore. The problem with this is that, according to Hawking's computations, and many after that, the radiation that comes out is perfectly thermal. So the only information it carries is information about the temperature of the radiation. So for the radiation, only information is the temperature. And also you can say more accurately that this means that you have something called a thermal state, which is something we describe using density matrices. So in quantum mechanics. So before we did all that, when we still had the star, when looking at this quantum mechanically, this star, you can say, is in a pure state. Which means that, which just is another way to say that it's just a type of quantum mechanical states we have learned about in quantum mechanics, right? But then it evolved through all this into a thermal state, or maybe more generally something called a mixed state, which is, just to keep it general, some sort of something in between a thermal state and a pure state. So it's not quite thermal, because maybe it carries a little more information than only the temperature, but it's not a pure state. So we are evolving this theory from a pure state into a mixed state. And this is not possible according to quantum mechanics. Because in quantum mechanics, if you take a state, and evolve it, then you use the unitary operator. Like this. Something like this, right? And you go from a state to a state, and you can go back in time as well by inverting the unitary operator as well. So if you start with a pure state, you always have a pure state. So there's something completely weird going on here, which means that you're left with two possibilities. So either somehow this is wrong, this is not the correct description of this scenario. So somehow quantum mechanics still works. Or the scenario I just described. But let me say that first actually. So quantum mechanics breaks down because you are going from a pure state to a mixed state, and if you think a little about that, what that means, that it is just another way of saying that you have lost some information. So the quantum state describing this star has much more information than the mixed state describing this photon radiation left from the black hole. So you have information loss in this scenario. So if Hawking is right, at least Hawking from around 1980 is right, then quantum mechanics breaks down. If Hawking from more like I don't remember 2003 or something, the more recent Hawking, if he's right, then quantum mechanics still works, and information is preserved. So how can this be? Well, this must somehow mean that there is the Hawking radiation carries information. That's at least the most generally accepted explanation for all this. That somehow it carries a lot more information about the state of the black hole than just the temperature of the black hole. Okay, so any questions to this?
But when can we read the information in Hawking radiation?
Well, that is, I mean, you know, the Hawking radiation has a certain spectrum, which close to the black hole, as I was saying before, is this black body radiation, and that gives you a formula for how the spectrum should look at all energies. So from extremely low energies to extremely high energies, right? But that is somehow not something. I mean, that is actually pretty obvious that cannot be true, because if you think of, I mean, if you take a black hole of some mass which emits radiation, then if the energy of the radiation is of order of the black hole, then obviously the black hole afterwards would be completely different. You know, you would go from like if you emit a very enormously energetic particle, you would change the black hole a lot after emission. And one of the crucial assumptions in Hawking's computation is that the radiation that you emit doesn't change the black hole geometry. So in other words, there's no back reaction of emitting this radiation. You just keep assuming that the black hole is exactly as it was. It's like some sort of heat bath that can keep the temperature being the same, but can keep emitting radiation in the approximation where you calculate this. I mean, in the computation where you calculate the spectrum of the black hole. So somehow it's fairly obvious somehow that in the high energy part of the spectrum, you cannot have a black body spectrum, and perhaps that's where the information about what's inside the black hole is stored. Yeah.
So in this first scenario, so it means that after the whole evaporation of the black hole, you will have a pure state.
Here?
Yeah.
Well, not according to Hawking. So this would, according to Hawking, this would be a mixed state. Because he would, I mean, at least the Hawking of 1980, I mean, because he would say this radiation is black body radiation, more or less, which only carries the information of the temperature, nothing else. And then it's a mixed state.
But according to this, the first possibility that you said.
Yeah, then it's a pure state. Yeah, that's a good point. So then, according to, I mean, this is like scenario 2, right? So scenario 1, you really go from a pure state to a pure state. So that's a good point. So everybody working in, say, string theory, ABS, CFT, and etc., would say this is right. There's still a few diehards that claim that this can still be true, but and that's fine. But the rest of us think that this somehow should work, and also Hawking at this point thinks that. Okay, maybe it's a good time for a 10-minute break. So yeah, like we can say to 10 minutes past 4.
No? Yeah.
So now I will actually go back to classical GI. So I leave quantum mechanics because I will go in a different direction now, and this will take the rest of the lectures. And this is to describe why, to describe black holes in more than 4 dimensions. And this is there's many ways to describe this, and I've chosen a specific way that hopefully will be illuminated. But first of all, we should ask why even bother to study black holes in more than 4 dimensions. So one reason is string theory. So string theory predicts that there's more than 4 dimensions, right? Then there's some famous phenomenological scenario. Where you have TV scale quantum gravity, for example, and other, and extra dimensions, and all kinds of cool things. Unfortunately, that hasn't been found at LHC, but that doesn't, I think, in my private opinion, means that it's not there, because it also took quite some time to find the Higgs, even if everybody thought it was there decades. So who knows? Could still be true. So there's this phenomenological scenario with extra dimensions. I mean, there's many of them actually. Then it's also interesting to learn about the higher dimensional gravity, because you learn more about gravity in general. And this you can think of, it's a little bit like studying young Mills theory with more than 3 colors, which of course has taught us a lot in the limit of large colors, like a large number of colors. Then finally, it's been found recently that, I mean, in the last 15 years, that higher dimensional gravity gives effective description of some strongly coupled non-gravitational theories. So, say quantum field theories with dimension less than or equal to 4. Of course, you can also go to high dimensions, but yeah, anyway. So, for example, the most famous example is, of course, the unequal force superhearing Mills theory in 4 dimensions in the ADS-CFT correspondence. But then, as I'm sure you know, there's many other correspondences out there, like with condensed matter theories, QGD, and Mills, many other things. But common to all of them is that the strongly coupled dynamics of these quantum field theories that are described by high-dimensional gravity and classical gravity. So classical gravity it gives you an effective action for these theories and strong coupled. Okay, so let's look at the similarities now. Between what you have in D equal 4 and D greater than 4 gravity, because many things are very similar or exactly the same. For example, you still have black hole mechanics, as I told you about. You still have Hawking radiation. In the same way, the black hole entropy, thermodynamics, etc. And you still have the information paradox. So if you could solve it in high dimensions, you would presumably also solve it in 4 dimensions. And then, in terms of black hole solutions, you could also, from some point of view, although this is not entirely correct, as we'll see, say that it looks like the same because the D equal 4 Schwarzschild solution generalizes to the so-called Schwarzschild Tangolini metric in D dimensions. So this looks like the following.
So what about the uniqueness theorem?
Yeah, I'll come to that. Now I'm at the similarities. So you see this looks pretty much the same as the Schwarzschild geometry, just you have some different factor d minus 3 here, which for d equal 4 precisely becomes the structure. And that's a d minus 2 sphere instead of the 2 sphere of the structure. Okay, and actually the Kerr black hole has a similar generalization. I will spare you the details. But the Kerr metric generalizes to the Myers-Perry metric. For the Kerr metric, you have rotation in one plane. So you have one angular momentum. But in higher dimensions, you have many more possible planes to rotate in. So over here you have rotations in t minus 1 over 2, and the whole number part of that rotation planes. And you have the same number of angular momentum. So from this point of view, it doesn't look like there should be any surprises, but that is not the whole story, because we also have the differences. So the first thing is that there's no general unique experience. Nobody found anything like the uniqueness theory we have in 4 dimensions that works for all dimensions. So there's some specific cases for static black holes where you have some theorems, and there's also the specific case of 5 dimensions, where you also have some theorems in some restricted cases. So it's very difficult to generalize the uniqueness theorem of 4 dimensions to high dimensions. And it actually, there's a big story of why that's so, but which I will not go so much into. But there's a reason for this, namely, as I will show you explicitly, there's many more kinds of black holes than the ones I just listed. So you can say there's a reason why we didn't find these general unique spheres in some sense, because you actually have a lot of more black holes. So this fact that you have a lot more black holes, you can say that means that a black hole is less unique than in 4 dimensions. And this you can make more precise because in 4 dimensions you can characterize a black hole spacetime using very few geometric invariants. But in high dimensions you find that there's new invariants of black hole spacetimes which changes as you go between the different types of black holes you have. So you don't know if you need more than these invariants that have been found in all dimensions, apart from 5. But at least you know that. So you know that it's necessary to specify all these new invariants you don't know if it's sufficient to characterize the black hole spacetime. So this is something, that's the rock structure in 5 dimensions, and then something called domain structure well, basically that is general for all dimensions. So these are new black hole invariants that at least you know that you have to specify. Then you don't know if it's enough. And this means that it's harder to characterize a black hole. You need to measure more, make more measurements to characterize the black hole. Then there's even more differences, because in high dimensions you have instabilities of black holes. And this is unlike in 4 dimensions, because it's been proven mathematically, so very accurate proofs, that both the Schwarzschild and the Kerr black holes are stable under perturbations. And this is not true necessarily for high dimensional black holes. And all this, you can say, means that unlike in 4 dimensions, where you can say the phase structure of black holes is pretty boring. I mean, you have sort of a 2-parameter family of black hole geometries, and they are always stable. So it's pretty boring in that sense. In high dimensions, it's much more complicated. And you have a very rich phase structure, also because you have these instabilities. So you can have a situation where one type of black hole is unstable and it decays to another black hole. And then what I will try to advocate is that the reason for all this, or the reasons for all this, is one reason is that there exist extended objects in high dimensions with event horizons. And the sort of the basic type of this is what I will describe in a second, namely the black peak rings. The other reason that is so complicated is that it's possible to have largely separated scales on the event horizon. So you can find some regimes where you have 2 scales on the event horizon which are largely separated, and this gives the possibility to make effective descriptions of black holes. And then this is what I will describe. I don't know, questions to this? Well, I mean, there's one more thing that I could mention. One result that I haven't mentioned, which is sort of both a similarity and a difference between black holes in 4 and higher dimensions. And this is the so-called rigidity theory. So in 4 dimensions, if you remember, the rigidity theorem stated that if we don't have a static black hole, well, let's say for any black hole, we know that if we have a stationary black hole solution, it's also symmetric under rotations. So if we have a time translation killing vector field, we also find rotational killing vector field of the geometry. This is called the rigidity theorem, and it was found by Hawking. But then people actually generalized this to higher dimensions. So they also found the same statement. But the point of this is that there's only, you see over here, you actually have only one rotation plane in 4 dimensions. But in higher dimensions, you have many possible rotation planes. Say in 5 dimensions, you have 2, and so on. So, but you only have the rigidity theorem in higher dimensions only provides a single rotational killing vector field. So there's a sort of there's a similarity, of course, an obvious similarity, but there's also an important difference, namely that you're not guaranteed to have rotational symmetry in all the possible rotation planes of the geometry. Okay, so then I'm going to start on what I call black p-frames. And these are neutral and static geometries. And the metric is simply found by taking a Schwarzschild black hole in d minus p dimensions and adding or multiplying with p-dimensional Euclidean space. So this gives the following metric. Where for later use, I've defined this n as the space-time dimension minus the brane dimension minus 3. That's just to make formulas look nicer. So that is the metric. And what is metric of? Well, first of all, it's a solution of the d-dimensional Einstein equations without matter. And it describes, the metric describes an infinitely extended brane So sort of geometrically, so you have an infinitely extended key frame. And it's with flat embedding of the world volume. I'll be more clear what I mean with that. So you should sort of imagine you have, you know, the higher dimensional analog of the plane, the three-dimensional analog of the plane that just is completely flat and just is infinitely extended. And then you have the longitudinal directions, which are these x1 to xp, which are along the p-brane, and you have transverse directions, which here are called r, and the angles plus one sphere. This is transverse, and this is longitudinal. You can also think of the time as included in these longitudinal directions. But if you look more closely, if you choose a certain point, like a certain value of all these x's, then you see that there's an event horizon. I mean, then it's just like this Schwarzschild black hole. So you have an event horizon with topology Euclidean p-dimensional space across S n plus 1. Yeah, so another thing one should be careful at mentioning when we put it here is that the metric here is not asymptotically flat. So this is not an example of a new asymptotically flat solution, but it's because you can see if you go in this direction transverse, then you can go far away from the brain. But if you go in the longitudinal directions, then you keep being at the same distance to the brain. So it cannot be an asymptotically flat measure. But nevertheless, I will try to use this extended object to find new asymptotically flat black holes, and this will be. I will have to go through some things before getting there. So first we have to understand. Before getting to that, we have to understand a little better the properties of these black T-frames. So I don't know if you like, we can also have a 5-minute break, and then I can go 5 minutes over time. Or if you are still awake, you would like a 5-minute break? No. Okay. Then I go on. Okay. no wild protests. Okay, so okay, so then I want to go on to something called the stress sensor for these black key rings. But in order to understand that, I actually have to go back to the black hole case. So before, this is sort of the subject for the coming thing, but I will actually start with going back to the zero brain case, which is the black hole, although now in d dimensions. And then I would like to understand that better, because if I understand that better, then I have a chance of understanding the key brain. So this is something which we had already in the first hour of the lectures, because now I consider localized matter distribution so some T mu, and it's some Newtonian or special relativistic matter that doesn't change the gravitational field that much, only in a very mild way. So let me introduce some coordinates for the background of this, the background geometry of this localized matter, which is just a flat space. So I will use the following coordinates. So the time coordinate, and then y1 to y minus 1. And then I will also use the radius, which is just defined as being the sum of all these y directions where the usual definition of the radius, right? Just in t minus 1 dimensions. And then this statement that the matter is localized, I would like to make precise. In these coordinates, because this means that the matter is localized within a ball of radius L. So we draw this ball, then somewhere inside that is all the matter located. Then, if we are at radial distances much larger than L, we can look at the contributions to the gravitational field that this matter creates, and then you find that the leading contribution comes from the monopole moment of the matter distribution. And only one of the components of the energy momentum sensor can contribute to this, and that's the 0,0 component. So the monopole moment simply consists in the total mass or total energy of the matter distribution. Then you could have, I will not use that, but just to tell you, then you can have the higher multiple moments because of course, if you only have this, it gives you, not necessarily, the matter is of course much more complicated than just this single parameter. So if you want to give a better description, more accurate description, you have to describe higher multiple moments of the meta distribution. And then, for example, as I told you yesterday, the next thing you would have to compute would be the angular momenta. So if we, for example, take the angular momentum in the 1-2 plane, so here there's many planes, but I just pick one of them, then it looks like this. And then since so you see, since when I integrate, I have the coordinates in here, then it's not the monopole moment anymore. So this is instead a dipole moment of the matter distribution. And you can find all kinds of higher moments as well. But what I will focus on is this monopole moment. And what this means is that if we want to have a rough description of a black hole, sorry, not a black hole, if we want to have a rough description of this matter distribution, just to really leading order, we can just simplify it to only contain the monopole moment. And then you can replace this more complicated matter distribution simply with only the monopole moment. And then the matter distribution is simply this delta function. With all other components being 0. So you can say, if you want to say it more in a more fancy way, you can say that you have, in this way, you have integrated out this length scale L, this length scale L, so, and you sort of approximated this just by point parts. Okay. And then the result of integrating out this is that you only have this thing left, this point particle mass. And then we're interested in the gravitational field from this. So like yesterday, I used the fact that I can approximate my geometry with Schwarzschild. So this is obviously not Schwarzschild. Minkowski space. It's getting late. I can approximate the geometry with Minkowski space, and, like in these coordinates. So this is Minkowski space, and then a small correction to that. And then, if you now choose something called the harmonic gates, so this looks something like this. Then you can write the Einstein equations in a very simple way. Because if you expand the Ricci tensor to first order in H, you find that the Ricci tensor is just -1/2, and then the box operator on H mu nu.
This is in the harmonic gauge.
In the harmonic gauge, yeah. So I chose a gauge choice for this correction, yeah. So the Einstein equations. In this gauge, so in general, of course, also in high dimensions, Einstein equations are this. So then you can take the trace and put R mu nu on the left hand side only, and then you have this. So if we use now this, we can write that the Einstein equations becomes the box operator and then as a -16 by G and G mu nu 1/d-2 eta mu nu.
So what's T
Sorry, what?
T alpha?
That's the trace of the energy momentum tensor. So G mu nu, G mu nu. So down here it's you use the Minkowski metric to find the trace instead, since you're working to first order H. Okay, so this gives a very nice way of writing the Einstein equations. And then if we assume that H doesn't have any time dependence, so we are describing static matter, then it becomes even nicer, because then we can replace the box operator with Laplace squared, so only including spatial derivatives now. The rest is the same. Okay, and this we can immediately solve using Green's functions. So I'll just write the result. So the result is that the following. In particular, we can look at the 0,0 component now. I mean, so we insert now this result here, and then we look at the 0,0 component of the metric. So when we only include the monopole moment, then we get this. So I should only put the monochrome moment here, then it gives a delta function. And some vector from this vector here. And down here, since there's a delta function, then this just becomes the radius. So I derived that this is 16 pi m d minus 2 omega d minus, sorry, d minus 3. Omega d minus 2 r to the d minus 3. And this, in 4 dimensions, is what I used in the first lecture, which can tell you what the mass of the black hole is. Right? So I hope this is roughly clear to you, because now I could generalize it to p-branes.
What's omega?
Omega.
Or
Sorry, yeah, so it's because omega comes in when you, from this Green's function, when you, you have this differential equation here. So when you solve this, you get this d minus 2 volume of the volume of the d minus 2 dimensional unit sphere.
So what happened in D equals 3?
Sorry, what?
In D equals 3?
Yes. Well, in d equals 3, well, we cannot really do anything of what we have been doing because in t equals 3, if you try to have a point particle of mass m, then you actually create a conical deficit angle. I think it's a deficit. And this is another way of saying, like if you have a conical deficit angle, then it actually means that this is a global property of your space-time that you have a deficit angle, and that means since it's a global thing that you actually are not really able to go far away from it. Like in this, I've been using that I can sort of integrate out the length scale of my meta distribution. But if you go to 3 dimensions, that is not anymore possible to make that approximation. You don't have this statement that you can go far away from something, and then the effects of it are you can neglect some approximation. And this is also, of course, because the effects will go like log r. Right? So, like instead of 1 over r in 4 dimensions, it's log r, the solution of this equation. So then you're in trouble. And that's why people don't really, there's not really a black hole in 3 dimensions. So I guess since it's 5, it's probably a good moment to stop. So tomorrow I'll go on to generalizing this to p-branes. So are there more questions? Okay, so let's start then.